Welcome class, myself Professor D.S. Rai, Department of Civil Engineering, BBD, IITM Lucknow. Today the course I will take up KCE 064 Foundation Engineering. Today lecture is lecture 35, in which I will discuss reinforced earth. References that I have taken here: Dr. B.C. Punamia, Soil Mechanics and Foundation; V.N.S. Murthy, Soil Mechanics and Foundation Engineering; Alam Singh, Soil Mechanics and Foundation Engineering, and some material have been taken from internet. The contents today I will take up design consideration. So, design consideration, there are assumption of design of reinforced earth. The pressure acting on the wall facing element without reinforcement is the same as that act on a rigid pavement retaining wall under the active state. The Rankine earth pressure for the active state holds good, due to which the failure plane makes an angle of 45 degree plus phi divided by 2 with horizontal. And third, the backfill is a granular and is non-cohesive. So, these are three basic assumptions for design consideration of reinforced earth. So, now come to the different design consideration. This is a diagram we can see here. This is a wall facing element, that is A and B. The height of A and B is h, and there are many layers or segments divided in h each. This is the angle, that is 45 degree plus minus phi by 2. This is Rankine's earth pressure distribution, and here is a reinforcement having a tension T I. So, we can see here in the figure shows a reinforced earth retaining wall A B of height h. When the wall A B rotates about a point A of away from the backfill, a failure surface AD, is formed, which makes an angle 45 plus phi by 2. So, we can rotate this whole thing about the A, then we will make a Rankine's failure surface like this way. So, AD is the Rankine's failure surface. So, the active pressure acting on the wall at its base is given by, this is the PA, and this is the active pressure, gamma HKA. Gamma is the unit density, unit weight, H is the height, this is the height, and K is the coefficient of Rankine's active earth pressure coefficient. The pressure distribution along the depth is assumed to be a linear, represented by a triangle ABC. This is a triangle A, B and C. and the total active pressure at the base of the wall per unit length of the wall is given by P A, that is the total we calculate the total area of ABC, that is half, this is the gamma h square, means height of the wall facing, and this is the coefficient of active earth pressure. So, this is the P A, that is equal to 1 by 2 gamma h square K A. Now, let us divide the height of wall into a number of a small unit of height h. Let Z I be the depth of any reinforcing strip M N. So, we can go back. So, this is the M N, this is the reinforcing element. So, and this is divided into H of different layers. This is 1, 2, 3, 4, 5, 6, 7, means 7 layers are divided. The total pressure on a strip Mn, the total pressure on a strip Mn is represented by the area A, B, C, D of pressure diagram with the average pressure Pi. The average pressure Pi is given by, this is Pi, this is the gamma, Zi is the depth, and K is the coefficient of active pressure of earth. Now, come to the, let us assume that reinforcement are placed at the interval h in the vertical direction, and interval s is the horizontal direction. The tension T I in the reinforcement M n is given by T I. Tension T I is given by P I is the pressure at ith divided by a area. So, this could be written as gamma Z I K A H into S. This is the H into S, where A is the effective area of a strip, H into S. So, proceeding in the same way, the tension in the other reinforcing a strip can be found. Noting the fact that variables in depth Z I at the depth of the strip increases, the tension T I in the reinforcement also increases. The sum of the tension in all reinforcing a strip is equal to total earth pressure on the wall of length S. Thus, the total T I, total tension, is the summation of I to n, where I is equal to 1 and n is the numbers. So, we can write it like S P A. S is the distance between the strips. So, S P A, the now we can calculate the length of reinforcement. So, let us find the length of reinforcement. The reinforcing strip attached to the wall portion A B extends well beyond the active zone into the backfill. The length M n of the reinforcing strip is neglected for computing the necessary grip length. For resisting the tension development in each reinforcement. So, the next is, in other words, the grief length L E lying in RHS of the failure plane A D and should be such that it resists the tension so developed with a suitable factor of safety. Let L E be the grip length required to resist the tension T I developed in the reinforcement strip I. Located at depth Z I, and that is equal to I H. Let F be the suitable factor of safety. If F I is the frictional resistance of the reinforcement of length L E located at depth Z I, we have F I is equal to F into T I, where F is the factor of safety against bond failure, usually taken equal to 2. If D is the angle of surface friction, we have F I will be equal to gamma Z I tan delta multiplied by surface area of the reinforcement. So, the grief length L E depends on the surface frictional resistance developed between the reinforcement and the soil. This resistance eventually depend upon the shape of the reinforcement. There are 3 types or shape of reinforcement. One is a strip, means it has length, it has some width, it has some thickness. Second is rod, round, maybe round, having certain diameter, and the sheet have a wide length and width as compared to thickness. So, these are the 3 types of reinforcement used in reinforced earth, that is a strip, rod and the sheet. The reinforcing strip, again let B be the width of each strip spaced at S along the length of the wall. Is it? The frictional resistance is developed on both faces. Frictional resistance will develop on both faces of a strip. So, it has been taken 2 times of the strip. Thus, F I, that is gamma Z I tan delta, here is a 2 means 2 faces, this is the width and this is the length. So, because we have taken bottom and top both faces, so it has multiplied by 2. So, gamma Z I tan delta into 2 B L E or F T I will be equal to gamma Z I tan delta 2 B L E. So, we can calculate L E, the length of reinforcement, that is F T I divided by 2 gamma Z I into B tan delta. This length L is vary with the depth Z I. Now, come to the reinforcing rods. We have discussed a strip. Now, reinforcing rod. Let reinforcement consists of round bars, each of diameter d and the perimeter of each bar is pi d. This is the perimeter and L E is the length. Hence, F T I is equal to pi d gamma Z I tan delta. So, L E will be equal to F T I divided by pi gamma d Z I tan delta. So, we can see here this is the L E F T I divided by pi gamma d. D is the diameter of the rod, Z I into tan delta. So, the third one is reinforcing sheet. If the reinforcement consists of sheet laid along the length of the wall, the surface area will be equal to 2 LE per unit length of wall. Hence, LE again here same LE will be equal to FTI divided by 2 gamma ZI into tan delta. However, it is common practice to use one single length LE is calculated with the respect to the maximum tension, that is T max, taking ZI is equal to H. So, the angle of surface friction delta depend on several factors such as density and type of backfill material, type and shape of reinforcement surface, etc. Usually, the value delta varies from phi by 2 to phi, where phi is the angle of internal friction of backfill materials. Now, sectional area of reinforcement. Let ARS be the area of reinforcing a strip oblique bar of a steel or metal, then ARS will be equal to Fi divided by FRST, that will be equal to FTI divided by FRST, where FRST will be equal to allowable tensile stress in reinforcement. ARS is equal to BT for the strip of width V and thickness T, and is equal to pi d square by 4 for the rod of diameter d. Hence, again ARS varies with depth Z I. However, it is common practice to make computational corresponding to Z max is equal to H and provide uniform reinforcement throughout the height. Now, come to the external stability of the wall. The external stability of a wall of a reinforced earth structure must be also considered. A reinforced earth wall, although behaving as a relatively flexible structure, should be designed as if it were a gravity wall from the point of view of external stability. The back of the wall should be taken as a vertical plane through the inner end of the lowest reinforcing element. The total active thrust on this plane should be calculated by the Rankine's theory. Now, the factor of safety against sliding between the reinforced fill and the foundation soil should not be less than 2. The angle of shearing resistance of the weaker soil being used in analysis. The pressure distribution on the base must be wholly compressive and must not exceed the allowable bearing capacity of foundation soil. All potential failure surface in compressing the structure should be analyzed. As for the slope and a minimum factor of safety 1.5 should be ensured. So, we have discussed the various points for design consideration of the reinforced earth, but one thing is important still, that is that depends completely on the site conditions, and we have to go a step by step for designing of this reinforced earth. One of the factors is that is considered, suppose there is a approach road of a bridge, where there two walls are confined together, in which we are providing a reinforcing rod or geosynthetic fibers also being provided. So, there are a confined area in which we have to provide. So, we have to go for design with a slightly different way, and the earth that we are using should be sand, non cohesive, completely non cohesive. So, that will give a better result. So, for this point of view, we will discuss it example in the next session, the reinforced earth. So, thank you very much.